Hey guys, my name is Boris and I'm a 6th semester computer engineering student at the Technical University of Berlin. And on this channel I want to talk about things that I've learned and might bring you value, general educational topics, and perhaps a few lifestyle videos. Do you know how heavy computation like tensor-based ones for machine learning, especially CNNs, or image processing pipelines, are generally performed on a bit more powerful machines that are connected to a endless power supply? Now think about how those calculations or similar ones are executed on edge devices like smartphones or VR headsets, which are constrained by power or, more importantly, battery consumption. Such devices even go into low power modes where they reduce the frequency of operation, thus increasing the time necessary for the computations. Now, what if you want to go into such a low power mode, but don't really want to wait twice as long for an image to be processed? Well, to achieve such speedups, approximations can be used. So, methods that are not quite as accurate as the original ones, but are quite a bit faster with a hopefully negligible accuracy loss. I want to go a bit more in depth on a quite recent paper that approaches exactly that issue, and most importantly wants to optimize the selection of the configurations necessary for the approximations to achieve the speedup. If this doesn't make sense yet, we'll go a bit more into that and explain it. Okay, so the main goal of Approx Tuner is to generate a trade-off curve so that at runtime the configuration of the approximations change, meaning become more active or not. For that, Approx Tuner goes through 3 stages: the development time stage, the install time stage, and the runtime stage, where, for example, Approx Tuner predicts the QoS, so quality of service and performance, of only hardware-independent approximations. And QoS is basically just the comparison of how bad the output with the approximations is compared to without. And in the end, you will have a trade-off curve that consists of triplets as points, with the configuration, the predicted quality of service, and the predicted performance. So I've been talking about those configurations a lot, but let me show you what those actually are. A configuration is a set of knobs that basically are the hyperparameters that define how an approximation should work. Let me show you a few of the hardware-independent approximations so that you get an understanding what those knobs are. Take, for example, perforated convolution, where you basically have an image with all its pixels and you want to apply a filter on top of it to highlight certain characteristics. And this filter would go over basically every pixel and evaluate it or work with it. Now, with this approximation, you can basically skip, for example, 1 in 2 rows or columns with an offset. And the skipped rows or columns are then interpolated with the mean of the neighboring pixels. And those choices that you have, skipping 1 in 2 rows or 1 in 3 rows or skipping columns, and what offset you have, those are the knobs. In this example, I chose skipping columns with a 25% skip rate, so 1 in 4, and with no offset. Approx Tuner offers 2 knobs to choose if you want to skip rows or columns. Then it has 3 skip rates: 50%, so 1 in 2, 33%, 1 in 3, or 25%. And with each skip rate, you have a specific option for an offset. So with a 50% skip rate, you can start in the first column or row or in the second. And for a 25% one, you skip 1 in 4, so you can start in the first, second, third, or fourth row. So overall, you have 18 knobs here, and this was only one approximation. Then there is also filter sampling, which is similar, just reduces the amount of filters overall in a operation, which then leads to 9 knobs. Then there's reduction sampling, which has 3 knobs. Then you can choose if you want FP16 or not, again 2 knobs. And then you would have hardware-specific approximations, if you know about promise, that's it. And this again has 7 knobs. So in the development time stage, Approx Tuner basically takes in a program and a minimum required quality of service, and then evaluates all operations with the approximations that can be applied to them. And for each operation and knob pair, it collects a profile consisting of the quality of service and the actual output tensor. And Approx Tuner does this by running the entire program with the applied one knob, and then measures the quality of service and saves the output tensor. Eventually, this tuner starts evaluating whole configurations, so sets of multiple knobs applied at the same time. And then it calculates the predicted quality of service and the predicted performance based on mathematical models, which basically again only compare the real quality of service with all the knobs applied in one configuration to the base output tensor, or rather the base quality of service. The paper actually offers 2 mathematical models, but let's just stop here. And the next step would be to compare the actual resulting quality of service for each configuration to the minimum required quality of service, which is given as an input by the user. And if the QoS, or the real QoS, is above the minimum QoS, then this configuration is added to the candidate list. After that, the algorithm creates a curve with the optimal choices for configurations. And with optimal, I mean Pareto optimal for the interested ones. And then it relaxes the curve a bit because it still is a prediction. And with those configurations, Approx Tuner now actually runs every configuration of the program, measures the quality of service and performance, and again compares it to the minimum required quality of service. And then we will finally have our final development time stage, trade-off curve, which again will be a bit relaxed because it still isn't applied to the end edge device. Okay, all of this was done with only the hardware-independent approximations and was executed on a server-like machine. Now we will get to the install time stage. To make it short, the curve is sent to the target device. This device then goes through a very similar process, but with an already reduced amount of configurations to evaluate, and can then measure the quality of service and performance now with the hardware-dependent approximations. The measurements themselves are done distributed among the edge devices, and the calculations are again outsourced to the server. But in the end, we finally have a valid trade-off curve. I won't go too much into evaluation, but I want to show you what happens at runtime. Let's take a neural network like ResNet 18. In the normal or high power mode, the device operates at 1.3 GHz and has a normal runtime for the execution of the program. Now take a look at the blue and gray graph. When going into a lower power mode, meaning when reducing the frequency, the accuracy stays the same, but the time necessary to execute the program is, for example, doubled. With Approx Tuner, when a loss in execution time is measured, a new configuration is selected so that the accuracy is dynamically decreased to generate a speedup, thus keeping the runtime the same. Up to a certain point, of course, where the user defined the minimum quality of service or accuracy. As for further evaluation, it works pretty well. And with that said, I would like to end the video here. I hope you could learn something and found it interesting. As always, thanks for watching, and I'll see you guys in the next one. Bye!